Okay, so welcome to the tutorial for information retrieval in high dimensional data. Today we have two things, like two main things at hand, and one is related to feed forward neural networks, and of course the other one is the new lab that we will discuss today related to principal component analysis. So let's start with the first one. And actually, this is because in the last lecture, while discussing back propagation, there were some questions by you guys, and it seemed that maybe we can spend some more time to see how this back propagation works. And just let me set up everything. So okay. Mm, so- yeah. So let's proceed. So what we are discussing today is back propagation in feed forward neural nets. Okay. So the first thing that you need to keep in mind here is that back propagation is very similar to the chain rule. Okay. So for instance, if you might remember, let's say we have a function f of x and y, that is, I mean, let's say there is anything like 2x square plus 3y square, let's say, like that. Okay, and we name this as equal to z. Okay, and then we have a function of z that is equal to, let's say, z cube. Now if we want to calculate the differential, or in this case like the derivative with respect to, let's say, x or y of this g of z, let's name this g of z equal to m, just for sake of notational convenience. So in that case we have partial of m over partial of x is equal to partial of g of z by partial of x is equal to g dash z. This means the derivative of z with respect g of z with respect to z. Okay, into partial of z with respect to partial of x. Okay, this is the chain rule in a nutshell. So now we know that now we can separately calculate this partial, which is 3x square, because of this z, this g of z was equal to z cube, so g dash of z is 3x square. And now here we see that z was equal to 2x square plus 3y square. So this term becomes partial of 2x 2x square plus 3y square with respect to x. And we know here the only term that matters is this x term, so this becomes 4x, right? So this is how the chain rule works. So in order to compute this thing, we go step by step through the functions, provided that all the functions are of course differentiable. So then it becomes like 3, I'm sorry, this should be 3z square. So this becomes 3z square into 4x. Okay, 3z square from this and 4x from this term, that we can see, we have seen that it computes to this. So this is like the basic chain rule in a nutshell, and I strongly assume that you are all already familiar with this thing. Now we move on to an example of neural nets. Okay, so we will see a simple example, but the whole theory follows in a very similar way for all the architectures and for all depths and all different numbers of layers and things like that. So suppose we have an input x1, x2, and x3, and maybe draw it a bit now. Just a moment, guys. Let's have a 2 minutes break because of this background sound, and we can proceed. Okay, so I'm sorry, guys, for this small delay, and now we will resume. So we have this input x1, x2, and x3, and suppose the first layer of the neural net consists of m1, m2, m3, and m4. So the way we can assume this is, yeah. So we have these three weights, and then we have weights going to m2, and then we have weights going to m3, and in the end we have weights going to m4. So what this means is, okay, I will let me define this right here. So this m1 is equal to w11x1 plus w12x2 plus w13x3. Okay. Similarly for all, let's say, like similarly, like m4 is equal to w41x1 plus w42x2 plus w43x3. So actually, on this, like every line has a weight. Like this line represents this every edge represents that we will be multiplying a weight with x, and then we will be adding up everything to get m1. So like this one has w11, and this one has 1 2, and this one has w13, and so on. Now this is the definition of m1, and now after that we have an activation function. This is like, this can be sigmoid, as we have already studied, or there can be other functions, but the main thing is this function acts on every dimension separately. And afterwards, let's name these results h1, h2, h3, and h4. This is like a basic architecture of the neural network. Okay, so this is right now, this is like the first hidden layer, so to say. Okay, this is when we say hidden like this is how we define the hidden layer of the neural nets. Maybe, yeah, this is the first hidden layer of the neural net, so to say. And then we have let's make a neural net with only one hidden layer. In that case, um, let's say we have here a function g. I mean, I could have written this also as a function here, but yeah, this is in fact a function of w1, w11, w12, and w13. So we have a function g here, and here we have weights, let's say mu1, mu2, mu3, mu4. And let's name, I mean, this is just different names that we are giving so that we know where we are when we are doing back propagation or forward propagation, so to say. So this is like a simple a neural net with one hidden layer. So we have inputs, and we have like different weights that multiply get multiplied with the inputs to give this m1, m2, m3, and m4. Then we have activation functions. We have kept them here abstract. Like this can be anything. I've simply used sigma function, and this results in the values of the first hidden layer. And then we this architecture, this thing, uh, yeah, this thing can be repeated again and again. Okay, so what we do is afterwards, let's say we again can have another, let's say m5, and again for it will have an activation function, and it will give us, let's say, h for the second layer. It will give us h1, and so on and so forth, right? So if we can go through this one small example, it should be more than enough to imagine everything, even in the deep neural net. So now after that, suppose that this is the output of the neural net, and when we are training something, we have when we train, we have pairs of input and output. So like we have seen that data set, like training data set has pairs of like x1, um okay, how to represent that, yeah, maybe like that, y1 true, and up to xn and yn true. So this tree means true. So these are the like the training pairs that we have. So what we want is, given this input x, we want our neural network to learn the true output y. But it is outputting right now we want to learn yt, but it is outputting right now y. So that's why we define a loss function which we minimize. And if this loss function is minimized, this means our neural net has been trained, at least on this training data. So right now, let's imagine a simple loss function. Let's imagine a simple loss function like y of like loss of y and y true is equal to mm, y minus y true square. I mean, since this is a scalar, we can simply use, yeah. Okay. So now the basic purpose, of course, of this neural net is to learn the uh, the weights that are involved in our model. So right now, can anyone please write down what weights are involved? What are the variables of our model? I am looking at the chat right now. Maybe if someone can help me here. Mm, so are you guys with me? If like maybe you can give me a quick thumbs up if everything is going fine. Then I will proceed. Okay. Yeah, okay. I got some thumbs up, and I also got answer from one of you guys, Jim Shaw, and like he has correctly answered that the weights involved are these W's and the mu's. So we need to train all these W's, and we need to train all these mu's. So these are the parameters of our model that we need to train. And the way back propagation works is we use gradient descent, as we already mentioned. So what we do is we know that like any function y, for any function y of x, if we use this a partial y or partial x, or if we derivate it with respect to x, it points in the direction of steepest ascent. So like let's say this is our function y of x, this is x, and this is y of x. And at this point, let's say if or yeah, let's say at this point, if we see the direction of the steepest ascent, this will be the gradient of the function, right? So it will point out, this will be the tangent, and it will point out at the direction of the steepest ascent. Now for if we want to go down, we need to look downwards. Okay, so in that case, we need to look downwards. This is, that's why it is called gradient descent. So we want gradients with respect to all the involved variables, and then uh, we want to update the variables slowly so that they slowly reach some minimum point. Like for instance, here we have this minimum point. This function might have another minimum point like here, but this is another story. So let's keep this. Okay, it will be difficult to keep it aside, but anyways. So we will, this is like a side talk, so to say. Now, suppose we need to find the derivative with respect to this mu11. So we need to find the derivative of the loss with respect to mu11. That means we want uh, delta of L with respect to delta of W11. Okay. So we want to update W so that it minimizes the loss. So this thing we will do with all the variables. We want to update all the variables one by one so that the collectively they are targeting the direction that minimizes the loss function. So this becomes equal to delta over delta W11, and the loss is y minus y true square. And now again, following the chain rule, we can here this is a variable, this is a true value. Of course this is not a variable, so what we can write here is delta of y minus yt square divided by delta of y into um, partial of y over partial of, now y is made up of y is, I'm sorry, I forgot to add here an activation function. I mean, we can add that or not, I mean it's up to us, but just to give you a better picture. So y, delta of y with respect to the involved variable, that is only z. Okay, so this thing is, as we know, 2y minus y true. Now we look at this thing. So we know that this becomes equal to delta of sigma of z over I should say partial, not delta, but anyways, you're getting the point. So we use this with respect to the involved variable. So sigma of z divided by partial of z, and let's keep it abstract, and this is equal to partial of z. But actually here I made a mistake. I should have written here w11, okay, to follow the chain rule, because like partial of this function with respect to w11 is equal to this immediate partial, and multiply by the partial of the rest with respect to w11. So here it is actually equal to w11, and now we have here, because of this we have partial of z divided by partial of w11. So you're getting my point. So what we did is we moved from, here we had loss, we moved from loss to y, from y to z, and now we are at this point, right? So partial of z with respect to w11, and we can see that z is equal to g of all these mu's. Okay, so again, when this was one of the questions and one of the confusions during the lecture. When we write, of course, as we write function, we write f of x, where this x is the variable, right? So here our weights are the variables. So we can write this as partial of g of mu1, mu2, mu3, and mu4 with respect to w11, right? This is the definition of z. As we can see, this z is equal to g of all these mu's. And in fact, we can explicitly write this if you want, like z is equal to g of mu1 to mu4, which is equal to h1 mu1 plus and so on plus h4 mu4, right? This is z. So now when we need partial with respect to this, now you can see, now our function is actually now our function has multiple variables, right? Now this is one of the points where Jacobian comes into play. So this right now, this is this differentiable, or this partial will not be a scalar value. This will be a vector value. So here we will write it. Uh, so here what we can again following the chain rule, what we do is we say this is equal to partial of g of, I mean let's write is add mu vector for simplicity, mu of mu with respect to mu and multiply by partial of mu with respect to w11. Okay, so this, and so now we are left with now we have if you are if you have any question till here, maybe you can let me know, otherwise maybe we can proceed. So this, if you see, this will be a Jacobian. Okay, this will be a matrix, and here the entries, the entries that will matter will only be so to say, um, in fact we have like yeah, we have added this separate step, but anyways, so the entries which will matter will be like for when we say partial of this with respect to mu1, it will be h1. When we say partial of this with respect to mu2, it will be h2, and similarly when we say partial of this function with respect to mu3, it will be h3, and similarly it will be h4. So you can see this, its Jacobian will be um, this whole this function with respect to all these variables, and it will be h1, h2, h3, and h4, right? And so this gives the value here, and then we have mu with respect to w11, and we know that what is mu. Mu is again let's say mu1 is equal to uh, mu I'm sorry, here we actually want to write h, not mu. Yeah, so this is something that actually I confused here. Yeah, because h is the involved variable here. So here we want to write h. So when we now when we talk about h, so we now from here we now we are at this position, and we can see that h is like h1 is equal to this activation function of m, and similarly h2 is equal to activation function of m2, and so on for h3 and h4, right? So now for this thing again we can see, let's look at the case h1. Okay, if we look at the case h1, is it is given by, and in fact we can let's write this down as h1 by 1 1, h2 by w1 1, and h3 by w1 1, and h4 by w1 1. And now if we see here, we get uh, so with respect to W11, if we see what is H11 with respect to with respect to W1 with respect to the immediate variable M1, H1 is equal to its like the activation function with respect to M1, right? So let's have a look at only H11 case first. So this is given by, so we can like we can simply write by using again the chain rule. We can again write like the derivative of function activation function with respect to m1 multiply by m1 with respect to w11, right? And now we have at last like uh, we are at last at the place from where we can directly see that the partial of m1 with respect to x1 is only w11, because we know that m1 is equal to w11. Oh, in fact we have already written that, here, right? So partial of m1 with respect to w11 is only x1, because no other term depends upon w11. So this results in this is equal to x1. And now the other thing is, if you look at h2, this will be given by sigma of m2, by following the chain rule, into m2 divided by partial of m2 by partial of w11. Now we can see that m2 does not depend upon w11, so this thing will be 0. Similarly for this thing, similarly for this thing, so we'll be only left with this h1 case. So what happened here is, if you can see, we actually jumped from every variable to variable. We calculated we calculated the gradient at the spot, and we following the chain rule, we kept on propagating backwards and backwards and backwards. Now here in this case that we discussed right now, we were lucky in a sense that from L to w1 we only had one path. Okay, suppose if we had multiple paths, for instance, suppose if there were let's say a weight that was connecting this m2 let's not talk about m2, let's talk about m1. So that was connecting, let's say, this m1 to g1 by like some weight, let's say let's say new one or anything like that. Now we would have two paths. Now when after reaching here, we would have to follow one of these, one path like that, and another path like that. Okay, and this will then and then the summation of these paths will give us the gradient. This is just like when we have derivative rule of multiplication, right? So we when we have two things to multiply, so we yeah, it's just like multiplication, or in fact here we can use it as addition, because this g function is in the end adding everything that is coming in to its way. So this is how actually the chain rule builds up, and this is how it we back propagate through a neural network. And now, but mu is a coefficient. Why not h? I'm sorry. Mu is actually the variable that we need to that needs to be optimized. Like it is one of the variables that needs to be optimized. I'm not getting the context of the question here from C. Lee. Yeah, maybe we can have, let's say, let's have a 5 minutes break here, or like we have 10-20. Yeah, maybe I can answer the question, and afterwards we can proceed. So, guys, welcome back after the break. And I guess this part was not recorded. So, let me just mention it once again. So, there was a small mistake here on my part. This should be g of h by, like partial of g of h by partial of h, because of this chain rule here. And I hope I have rectified it everywhere. I changed it here, and changed it here, and changed the corresponding Jacobian. Now, yeah, if there is if the problem, if I have written it somewhere else and forgot to change it, yeah, maybe you can let me know, or maybe you can change it yourself. Yeah, maybe you can let me know, so I will then rectify that. So now this is this is how we optimize with respect to a single weight, so to say. So we simply move backwards through the path for every we simply move backward through all the points, through all the stages, or whatever you want to go, through all the hopes, and we keep going backwards and backwards until we reach the variable of our concern. Now yeah, now the next thing is to vectorize it. Okay, so the way we usually do it, you see, we have these vectors w1, like these vectors, you can already see that these weights look like forming a vector notation, right? So in that case, what we do is we can like we can make a matrix out of them. Let's say we can say that this is the weight matrix of layer 1, and we can say that it is equal to, so we had three outputs, so w11, w21, and w4. 4. Let's be simple. So W41, and we had three inputs. So W12 and W13, and W42 and W43. Okay, so this is now the weight matrix, and similarly our X is now X1, X2, X3, and now we can say that age, I mean, let's say age is equal to sigma of X transpose W, right? So X transpose W will have now four columns, and this sigma will be applied one by one to uh, every output, right? As we can see here, it is being applied to every output. So this means, in other words, like we can say that maybe where was it? Yeah. So this, if we look from the figure, this is equal to the m vector, and then applying this activation function on this m vector gives us h, right? And similarly, we can now looking at the next layer, we can again calculate y as y is equal to sigma of what was that, h transpose and mu, right? So here we have h transpose as a single vector, and mu is also like a vector, like consisting of mu1, mu2, mu3, and mu4. So this will give us a scalar, and we can see that this was equal to z in the figure. If you see, I guess it was z. Yes. So this dot product, this on this in this part gives us this z, and then we use it like use the activation function, and it gives us y in the end. So this is the simple assembly that our neural network boils down to. So in the end, it is just how we say like vector calculus, so to say, and which calculates through which we can calculate the gradients. So yeah, so like gradient with respect to mu, yeah, gradient with respect to mu here will be equal to delta of h, and similarly gradient with respect to uh, with respect in fact it will be a bit more involved, because it will first we will need the gradient of activation function, and then we will calculate the resultant gradient. Yeah. So first we will calculate the gradient of the activation function, just the way we saw here for one element, and then we will calculate it for all. And okay, now the thing is, I will actually recommend you to go through this, okay? And you can already find on Wikipedia and on like different many other sites the equations for calculating gradients with respect to vector calculus, okay? And I will really recommend you to go through these, and we have simply two simple cases, right? So for example, if we have like x transpose u, and its gradient with respect to x is equal to mu, and similarly its gradient with respect to mu is equal to x, right? And you will find this if you search matrix calculus or vector calculus. I'm actually assuming you already know this. So if you see the gradients, and if you match them with a particular, with let's say with maybe you can try them with maybe W22, let's say, and you will see that in the end the result boils down to the same thing if you do it like through back propagation one by one, and if you do this matrix notation, because in the end, in the matrix notation, we are simply stacking up everything. So I would say, using a single weight, e.g., I don't know, W23, let's say, and using matrix notation. Of course, these two should come out to be the same, and then yeah. So first we find the gradients using matrix notation, and then we find out then we target the element of the result. Like let's say we have like three dimensional vector in the end of the gradient, and we target the third element, and it should be the same as the gradient that we found out from this whole method manually. So that was it all for back propagation. Okay, HW means, yeah, let's write assignment. I mean, this is not graded or anything. This is just for your interest. HW means homework. So, yeah, but you can consider it as homework or like a voluntary assignment, so to say. But it will clarify a lot of things. And we still haven't introduced bias terms, bias weights, so to say. Usually, in fact, always in the neural net, what happens is with every with every weight vector here, which comprises of this all W1, W2, and W3. Uh, we also have here bias terms. So here we have like four, and so we have B1, B2, like every linear. This example was the example of a linear layer, as they say. So here we would have these bias terms attached to every uh, to every output. So we have like now we have actually, let's say this M1. Now we can say that M1 is equal to W1 transpose X1 plus B1. Okay, now we have this form. Before we were only talking about W transpose X1. So this is the linear layer, so to say, and this way what we do is we stack all like M1, M2, M3, and N4, and in the end we have this weight matrix. Like we in fact we can write that in the better way as for same notation X transpose W1. So then by stacking them up, we get this X transpose W1, W2, W3, and in fact, yeah, W1 X transpose, yeah. So these are like these vector W2, W3, and W4, and now we get this matrix notation which we call W, and then we have this B vector with us. I'm sorry, here we only need W3, and then we have this B vector with us, and this is how B1, B2, B3, B4. This is how we get this matrix notation. Yeah. So X transpose W1. No, I'm sorry. I actually confused it here. It should be transpose, and it should be B1, B2, B3, and B4. It should be like that. So yeah. So again, coming back to this case, you can. I would say I would really recommend you to go through this assignment once and see for yourself, and it will really clarify a lot of doubts if you still have any. And I would say we make a small break before moving to the assignment. Let's meet at 10:40. Okay, so we have like 3 minutes break now. So welcome back, guys. If you can hear me, please give me a quick thumbs up so that we can proceed. Cool. Okay, so now the assignment for today is related to PCA, principal component analysis, and yeah, it is actually rather a simple assignment, I would say. So let's go through the tasks. So the first task is, in this task, we will once again work with the MNIST training set as provided in Moodle. Choose three-digit classes, e.g. 1, 2, and 3, I mean anyone that you want, and load 1,000 images from each of the classes to the workspace. Store the data in a floating point matrix X of shape 784 by 3 into n. So why 3 into n? Because we have like n is equal to 1000 and we want to have three classes. And why 784? I guess 784 is like just like if we multiply, if we multiply 28 by 28, I guess it is 784. Yeah, so it is 28 by 28 dimensional. These images are 28 by 28 dimensional. So we vectorize the images that we get from the directory. That's why in the end we will get this shape. And then we normalize it by dividing it by 255. You already know the usual drill. And then furthermore generate a color label matrix C of dimensions 3 into n by 3. So each row of C assigns an RGB color vector to the respective column X as an indicator of the digit class. Choose 001, 010, and 100 for three-digit classes. So this is just for coloring because we want, in the end, we want to plot and we want to see where different elements fall in the plot, where different digits fall in the plots. So the first task is compute the row-wise mean mu of x and subtract it from each column x. Save the results as xc. So you might have seen we did this before. We also did this before. So now it should be in your mind that this is like sort of whenever we work with PCA, we first sort of make the data centered, so to say. And so the here this is the like the normal code which we have simply like chosen three digits, 1 2 and 3, and this is simply like following the directory pattern that we have, and we load 1000 digits from each class, 1 2 and 3. That's all this code is doing. So we define a placeholder matrix for the digits, and we define a placeholder matrix for images. So we have like yeah, so because right, this by 3 into n, because we will have in the end 3000 images, and every image will have a class based upon the digit, and we will be using one hot encoding as was told in as we were told in the this PDF of the tasks. So that's why we end up with 3 into n by 3 size for colors. So what we do is this enumerate function actually returns not only the digit prefix but also the index, so to say. So for example, this it will return here it will return 0 and d1. So this tuple will be 0 and d1, then 1 and d2, then 2 and d3. And then we find then we define this is just one hot encoding. So we define a zero vector of size 3, and we make the respective index I equal to 1 just for one hot encoding. And then for every class we will loop through 1000 times, and we will load 1000 images into our X. And this is just for how to say uh, like jumping through the indexing the X vector. So here you can see we are here revealing that we're flattening our X, so that 28 by 28 now becomes 784. That these all dimensions go here, and this controls the next index of the X. And you can see the indices are the same. So yeah, this code is mostly self-explanatory. Then what we do is we find out mean, and we afterwards we subtract the mean from X, and we use this expand dimensions just to, yeah, we have already written that just to ensure correct broadcasting, so that we know the mean is subtracted from the right dimensions. And in the end we have the same X shape as we were asked in the assignment. Now, the next task is to use np dot linear algebra, like li and alg dot svd. This is the same thing that we have already used, with full matrices is equal to false, to compute the singular value decomposition mu sigma and v transpose of xc. So we want to find out SVD of the centered matrix. Make sure the matrices are sorted in descending order with respect to the singular values. This is already done by this function SVD, so we don't need to worry about that about the sorting here. But this is a usual practice that we need. We usually double check that the results are arranged in such a way that okay, like in the SVD, let's write it here. So in the SVD we have mu, sigma, and V transpose, right? So okay, now while we are at it, let's see if let's say our X is of this shape. So this is, let's say, n by m, and its SVD becomes n by n, n by yeah, okay, I am confusing something here. So we have n by n, and here we have n by m, and we have here m by m. Yeah. So this is mu, sigma, and V. So this sigma, like we have this in the diagonal form, and of course, if like n, I actually did not plot it in a visually good way, so to say. I should have made it a bit clear, man. Just a moment. So we have n rows and we have m columns like that. So this is our sigma. This is the diagonal, and here we have 0, and this is the m by m part of this is the V transpose, and this is the sigma. This part, as we say, and here we have like these values: sigma 1, sigma 2, up to sigma n. I mean, depending upon whatever we choose, sigma k, let's say, or yeah, oh sorry, this is sigma m, because m is right now smaller than n. And again, it is actually a bit more involved than that. It depends upon the fact that we have the rank is not smaller compared to m and all that, but we haven't discussed this in the lecture, so probably let's skip it here also. So this is also n by m, and this is how it is right now. So what we need to usually ensure is that this value is greater than this one, and similarly this value is greater than this one and this one. So this is the descending order that we need to ensure. So this is not very difficult. We simply find the like largest value. Suppose the second value is the largest value, we shift it here, and accordingly shift these columns and rows also in accordingly. And in the end, because these are just orthogonal basis, or orthonormal basis, as I say, these are just orthonormal basis, so it doesn't hurt to shift them, so to say. So this is what we were asked, but we are lucky here that in our case, this function already does that, so we need not worry about that. So we're getting U, sigma, and V transpose from SVD, and we are like this line is enough to perform all the SVD, like the whole SVD. And now what we want to do is use reshape to convert mu and the first three columns of U into 28 by 28 matrices. Plot the resulting images. What do you see? So uh, yeah, okay. This is something that I need to see why I didn't show. Yeah. So I probably didn't run all the commands above. So now what we are doing is we are simply like using this subplot, like one row and four columns, and we're picking up the first spot here, and here we are simply plotting mu, and then we are plotting the first column and the second column and the third column of the U matrix, like the three basis vectors, so to say, orthonormal basis vectors from the column space. And yeah, so this is just for your visual purpose. As you can see, these are a bit more involved. You can see, for example, this one is very clearly telling that this one is very biased towards 3, so to say. This one is very biased towards 1. This one seems quite biased towards 2, right? So for instance, you see this, I mean, if we are we can even visually we can get a brief idea that this u2 is probably highly biased towards 2, and it is trying to subtract the information of 1. So this is a clear dimension that it is following. And similarly, we can see this 3 is bright, and we can see a dark shadow of 2 backwards. So usually these are not that much visually clear, but here we are, I mean, a bit lucky that we can even sort of make a visual sense from these vectors. So now and now the next step is compute the matrix uh, np dot we want to now compute sigma into v transpose, okay. And now we are saying that this is the same as transpose into x, okay. And this again we can see very easily. You might remember this comment was already made by Umar during one of the lectures, I guess the one before the last one. So you can see, if we say, just a moment. So here we have u transpose into x, right? So if we use um, u transpose into x, and if we use SVD of this x, we have u transpose u sigma v transpose, right? And these are orthonormal normal, so we have identity here, and we are left with sigma into v transpose. So that's why we can say that this is equivalent to this thing. And the good thing is, here we need to multiply with the whole vector. I mean, these are dense matrices, so to say. And here we know that this matrix contains either diagonals or zeros. So that's why this computation is like, this is computationally quite like this one is computationally quite a lot feasible compared to this mu transpose x computation. So now we come back, and we do this task D as we've been asked. And the S matrix, we name this matrix S matrix. The S matrix contains the 3n scores of the principal components 1 to 784. Create a 2D scatter plot with C as the color parameter in order to plot the scores of the first two principal components of the data. So yeah, this is what we are doing here simply. So we are ordering the indices for visualization purposes, and then we are plotting the scatter plot. So scatter plot, simply we give x-axis in the first as the first argument, and the y-axis as the second argument, and this C is the color index, so to say. And then we make a scatter plot, and we can already see that we had you see we had 28 by 28 dimensional images, like 784 dimensional images. And using only three dimensions, only like using only three vectors, only three basis vectors, we were able to extract so much information that we can even visually see that there is a sort of these classes are have a visual split, so to say. Even like we can see, for example, this one class, I don't know if this is 1, 2 or 3, but like it is biased towards this like towards the left, so to say. This blue class is biased towards top, and this green class is biased towards bottom right. So we can already see this is the power of PCA, that using only three like that using so few vectors, we can have a good representation, because we were able to capture the gist of data to a lot of to a large extent, as we already saw from the basis vector here. So the task 2 is, in this task we consider the problem of choosing the number of principal components. So the next thing now that comes in our mind is, okay, now we are reducing the dimensions of the data, but how much should we reduce? Okay, so how much if like how much number of basis vectors should we choose that we get enough information from X in this transformed space. So this is the question that now we will look at in this task. So what we do is, assuming X is P cross N is the centered data matrix, and projection is UK U transpose, this is the same like the definition of projector. into k dimensional subspace, the dimension k is chosen such that the fraction of energy does not exceed epsilon. Just 1 second, we will resume. Yeah, so we are back, and I'm sorry once again for this background um, announcement. Yeah. Okay, so anyways, let's proceed. So what we are what's our aim here? The aim is when x is projected to this column space that is defined by the first k columns of the U or the loading matrix, then we want to see that we want to ensure that the difference between the x and the projected x should not be should not increase a certain threshold. Okay, so this is the way we define energy. And when we so we take the Frobenius norm of the numerator and denominator. This is simply to how do we say, simply to normalize the value in the numerator. So this value will be between 0 and 1, and we want to see that what is like how much uh, tolerance, so to say, we can bear when we are when we are transforming x to this subspace, this projected this subspace which is defined by the first k columns of the loading matrix. So this is again same as this thing. We have already seen that Frobenius norm can be written in this form. This was probably first or second lab, and yeah. So if let's say if epsilon is 0.01, this means we are targeting that this difference should be less than 0.01. That means 99% of the energy value, so to say, should be preserved. And if it is less than 0.2, this means we are saying okay, zero at least 80% of the energy should be preserved. So this is what this means. This since these are in fractions but not in percentages, that's why we have this as 1% and 20%. So for this purpose, we take help of MIT Viztex database. And by the way, I haven't uploaded that in Moodle. And yeah, interestingly, no one of you guys also asked me. So probably, yeah. Anyways, it was actually greater than 100 MB. So I was having a problem uploading it because the limit right now is 100 MB. But I will see if there is a way to do that. I will try to do that after we are finished with this lab. So what we want to do here is we have 167 images, okay, and every image is 5 by 512, 512, and 3. That means like width and height is like 512 by 512, and it is three dimensional. That is RGB image. So now we don't have grayscale images, but we have RGB images, so to say. So we want to download it and unpack and familiarize with the directive structure. After that, what we want to do is we want to divide every image in that 64 by 64 tiles. So in other words, what we want to do is like we have this image 512, 512, and if we see 64, yeah, really bad in maths. So 512 by 64, it is 8. So like we will have like something like 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5, 6. This is like first, second, third, fourth, fifth, sixth, and seventh and eighth. So it's like we want to divide the image like that. And as a result, we will have of like 60. We will have p is equal to 64 by 64, and n will be, so width will be divided by 64, and height will be divided by 64, and as a result, we will have like this much number of images. So 167 into like this, yeah, 8 into 8. So this is exactly what we are doing here. So the first step here, I guess we have mentioned that. Um, it should be mentioned in the PDF. Yeah. So the first step is to make convert them to normalized gray uh, images, gray matrices, so to say. And the formula, the simple formula that we have used here, this formula preserves the luminance, I guess. Yeah, this comes from, this is like a standard formula if we have RGB images, and if we want to preserve, uh, like if we want to convert them to grayscale. So so this is like a standard formula which computes the luminance from RGB values. So we simply report luminance, and we use this as grayscale images. After that, so this was the function that converts to grayscale. So we, from the directory, every file is ppm file, like jpg or png. These files are ppm files, and we find the length of files. So this globe actually sort of lists all the files in the here in the directory, and we can see length of the files. And now we define this p and n, and as we were asked in the PDF, and we initialize the placeholders. So p and n is like x will be p and p cross m. And yeah, then what we do is we simply we simply read every image, we convert it to grayscale, and then we have this 8 by 8, because we saw if we have 64 by 64 grid, like if we have 64 by 64 tiles, this means we have 8 by 8 splits, so to say 8 splits in rows and 8 in columns for the images. That's why we run from 0 to 8 in both in rows and columns. And we add this, we flatten that tile, and we add this um, here as p, as we have seen here already that p will be 64 by 64 now, not 512 or 512. So we are like making more images out of 167 images, so to say. And after that, we calculate mean, and we make the data centered by subtracting mean from that. And then again, just like we did before, we calculate SVD from these images. And afterwards, yeah, this was task B. And again, we were lucky that they were already sorted in descending order. So the next thing is we want to plot the signal energy contained in the projection error. So as we saw, this is what we call the projection error. So now we want a plot with number of dimensions and projection error. So how this value changes with this k. This is what we want here. So how many principal vectors do we need to retain 80%, 90%, 95%, or 95% of the original signal energy? So this is now what we want to see. So for that, what we do is we have we have 64 by 64 dimensional image. This is I guess 4096. 64 into 64 is 4096, and then we define a range from 0 to 4096. We use +1 because we want to go till the last dimension. And then we calculate the projection error as was defined here in this part of the PDF. So we sum over all, like from I is equal to 1 to m, and we calculate a Euclidean distance with from the xi and projected value of xi. So this is what we are doing here. Yeah, and yeah, so we use one minus because we want to, of course, invert the results. Not we want to look in terms of zero, like 80 or 90, not in terms of 0 0.2 or 0 0.1. And after that, so as you can see, we calculated this projection error for all possible case. So we started from zero, and we went till 4096, and we calculated the total projection error for all the case. And then we plot this against the dimension and projection error. And now we see how much is the number of dimensions required to preserve 80% of energy, 90%, 95%, and 99%. So what we do here is we simply see where the projection error is greater than 20, and we find that dimension here by this like adding +1. And we can see that if we only stick to 98 dimensional K, we have 80% of the energy already preserved. So this is quite remarkable, I would say. So the original dimensions were 4096, as I guessed from here, because it is greater than yeah, 4000 here. So for 98, so 98 is probably yeah, it is somewhere here. Yeah. So if we can see here, it is like it is so less number of dimensions compared to 4096. It is like order of magnitudes less, and with this much number of dimensions we already are preserving 80% of the energy. So and if we want to preserve more energy, we use like for 90% preserve energy preservance we need 335 dimensions, still quite less compared to 4096. Similarly, as we increase our threshold, as we increase our demand, of course the number of dimensions keeps increasing then. So if we want to preserve 99% of the signal energy, still we want less than half. So like 4096 and its half is like 2048. Yeah, I guess 2048. So and we need only 1651 dimensions. So it is still quite less compared to the actual number of dimensions in X, and that too with preservance of 99% of the signal energy. And this means that this is how we sort of we can achieve dimensionality reduction using PCA. And in fact, in many cases, preserving, let's say, around 95% energy, or even 90%, or maybe 99% can even 90, like let's say 99 95% preservance should be actually better, because what happens is many a times our signal is intermixed with noise. So if we are preserving 95% of the energy, we are automatically reducing the amount of noise in the resultant data. So when it's a win-win situation. We are not only preserving, we're not only reducing the amount of noise, but we are also reducing the dimensions. Now there is a last task that says, can you imagine a scenario where signal energy is a bad measure of useful information? Yeah, so there can be like multiple many scenarios like that, but here we have mentioned a typical situation. And this usually arises in a case of this image processing, when the lighting is not coherent, so to say, and the lighting conditions are very different, so to say. And we have like already I have already mentioned that in detail here. So often the overall brightness of a picture does not add any discriminative value to it. For instance, a face recognition system should not care about whether the picture was taken at day or night. However, the overall brightness over a set of images that is processed, however, if the overall brightness varies over a set of images processed by PCA, the first principal component will mostly contain the brightest information. So this means, like for instance, in case of image processing, if we are designing a face recognition system, we can see that PCA, using this approach that we did, we can see that we like PCA takes into account PCA keeps the brightness information as a priority here, using the approach that we followed here. As a result, as a result, the decisions are I mean, the most important dimension that given by PCA is the one that contains most information related to brightness. But this is not what we are looking for in face recognition system. We are looking for an algorithm that finds different features of the face. For instance, if nose is sharp, or like how what is the structure of lips, and if what is the structure of eyes or eyebrows and things like that. Is the face round, or is like the face sort of say like a bit oval, whatever way we call it. Like we want an algorithm that preserves this, that understands the features and the relative difference in the features of the face, not an algorithm that differentiates between the faces based upon whether they were taken in days or nights. So this is a particular scenario where this energy can be a bad measure, because energy in the gray scale is like the difference between the brightness and the darkness, right? So if we have like one pixel is, let's say, at value 255, and another pixel of the same phase is at value um, if the same phase, exactly the same texture, the same picture taken at light, the same pixel might have value 100, so to say. So for PCA, this will be a lot different, because it is right. It is sort of making decisions based upon the brightness value or the energy value, as we defined here as our loss. So that was all for the second assignment, and not the second assignment, but like the PCA related assignment, but the second task that we needed to do in our lab today. So I will now stop the recording, and yeah, maybe if you guys have some questions, maybe let me know. Yeah, we are here. Otherwise, we can say goodbye.